welcome to the University of Illinois Chemical Engineering and Biomolecular Engineering Department. This is our newly renovated Theory Center, and I'm Lily. I'm a third-year PhD student in the SYNC group. Follow me! So this over here is the SYNC group research office. So this is the student office where we normally do our work. Of course, given the pandemic, we're currently working remotely, but this is where we would be working in normal times. All right, and then another part of the Theory Center that I'd like to show you is our conference room. Where we can hold group meetings, we have a large TV, we have whiteboards where we can have discussions with our advisors or anything. We also have a kitchenette area. Right over here where you can, if you want to bring your own lunch or store it or whatever. And we also have a little bit of a social area over here in the Theory Center, and more boards so that we can keep on writing a bunch of equations. And then of course next door is the Baron Peters group. And if you go that way, you'll see the Shukla group offices. All right, that's it for me. Thanks for joining.
All right, so the way we go about tackling problems is if you were to join the SYNC group, what would happen is he would assign you with an interesting problem that he wants to look at, and as well as the methods by which you're going to solve that. Now, well, it'll be your job if you were a member of the group to implement develop the model and then implement it, which means writing code. So we do delve a lot into physics, and there's a lot of math. But a big part of what we do is obviously going to be writing programs to run the models. Now, the first thing I would say is that you really don't need any computational research experience to join the group. Most people actually don't have that. You'll, just like with any other lab, you're going to have a few skills that you're going to have a lot of time to perfect, and programming is just another one of those tools. All right, so I'm going to show you exactly how this workflow looks like for me on this particular project. So if I open up my code here, so what I'm showing here is going to be the field theory that we developed, and so it's going to get a bunch of inputs, and it's going to give us the information we need to determine solution behavior in our system. And so this theoretical model that we have requires some information that we cannot get from theoretical approximations. And so to be able to get that, we also develop a different code that runs a simulation that's going to get us the information that we need. And so that I'll pull it up real fast here. Again, it's nothing we do is requires thousands and thousands of lines of code, but you can see here if I scroll all the way down, it's about, again, 500 lines of code. So you spend a lot of time trying to get this to work, and there's a lot of testing, a lot of debugging going on, but once you do have a working model, then what you can do is, so for instance, for this project I need to run this code about 3,000 times. And so, of course, that's never going to happen on my computer, but what we do have is a computing cluster that's actually located in the School of Chemical Sciences building, which is Noyes Lab. We do have quite a bit of computational resources. However, the work we do is it's not very computationally intensive work, because we're not really looking to replicate chemistry, we're trying to understand physics. Well, what you end up doing if you work in this group is you do a lot of code development, writing software, debugging, troubleshooting, but then there's also the other aspect of it that comes after the simulations are done running, which is data management and data analysis. So I'm going to show just a quick visualization of my simple simulation. You can see just polymers moving around. It's not that interesting, but this is another important tool for us because when we're troubleshooting our code, we need to make sure things are happening that we think are happening. And the other point is in scientific communications, it's really hard for people to understand just looking at equations what's happening in our system and stuff. So we have to spend a lot of time trying to figure out how do we explain the physics of what's happening. And so what we do a lot is drawing cartoons and making cool visualizations like this so that people can actually see what it is we're talking about. And speaking of scientific communication, one of the big goals, of course, is to produce research for public consumption, which mostly comes in the forms of papers, but as well as also conference talks. We do spend a lot of time, obviously on the computer writing programs and stuff, but we also spend a lot of time reading the literature and just developing. Model development is not just writing the code. The more important part is how you tie it from the basic fundamental principles of physics and statistical mechanics to get something that you can use in a model. And on that end, we work very closely with Charles. He's always willing to talk to you, especially when it comes to the more technical aspects of our models and the physics behind it. Gil and I hope to see you soon here at Illinois, or if not, I hope you find a school and a program that makes you happy. Goodbye.